Homework 10, section 5.3, independent events and the multiplication rule. Video 7. Joint probabilities, or probabilities involving the word and, can get a little tricky depending upon whether or not your sequence of steps involve replacement or not. Sampling with replacement versus sampling without replacement. The name says it all. Sampling with replacement means when you choose something, you put it back and it can be chosen again. Sampling without replacement means when you choose something, you don't put it back and therefore it cannot be chosen again. A classic example comparing the two is being dealt two cards from a deck of cards, such as you're playing Texas Hold'em and they give you two cards to start with. You're dealt two cards. What is the probability they are both aces? Well, first we need to determine is this with replacement or without replacement? So think about me giving you two cards. I give you the first card. Now, before I give you the second one, are you going to put your first card back in? Of course not. Then you wouldn't have two cards anymore. So being dealt two cards is an example of sampling without replacement, because you are not replacing your first card before you are being dealt the second card. So this is sampling without replacement. And I'll tell you right now that sampling without replacement creates dependent events. You'll see why in just a second. Actually, I can explain why now. When I give you the first ace, how many cards am I choosing from? 52. Now let's say I give you one of those cards and it may or may not be an ace. When I give you the second card, how many am I choosing from? It's not 52 anymore. I took out a card, so now it's only 51, which means my second fraction's denominator would be out of 51, whereas the first fraction would be out of 52. So they are dependent events because it's going to change the probability. So we want to know the probability that the first card is an ace and the second card is an ace. Now, if we do the multiplication rule for dependent events, it's the probability of the first event, so the probability that the first card is an ace, times the probability of the second event, given that the first event has already occurred. The first probability is pretty easy. Out of the 52 cards, there are 4 of them that are aces. But for the second probability of getting the next ace, we have to assume that one of the aces has already been removed. So I've already given you a card and it was an ace. Now, before I write that, I want to elaborate on this fraction over here. There are 4 aces out of 52 cards. Now, since this is sampling without replacement, there are no longer 52 cards left. I took one out, I did not replace it. There are only 51 cards left. So 51 remaining cards. Of the 51 remaining cards, how many remaining aces are there? It's not 4 because you already have one of them. So there were 4, you have one of them, which means now there are 3 remaining aces. And again, this is specifically because this is without replacement. We did not put the first card back. It's gone. So is one of the aces. By the way, both of these fractions will reduce. 4 out of 52 reduces to 1 over 13. A lot of people don't know this, but 51 is reducible by 3. 51 is 3 times 17. So the second fraction will reduce to 1 over 17. And if I multiply those, I get 1 on top. 1 times 1 is 1. And 13 times 7 is 221. What's that as a probability? Pretty small. Well, it is a probability. What is it as a percent? This small, 0.45%. So you have less than a 0.5% chance of being dealt 2 aces if you're dealt 2 cards. For those of you who do play Texas Hold'em, this means out of every 221 hands, you can expect to get a pair of aces once. That doesn't mean that if you've gone 220 times without aces, the next one will be. Because remember, probability is saying what percent of the time something happens in the long run. In the short term, anything can happen. No kidding, I was playing poker one time, and in a span of 30 minutes, I got aces 5 times. Everybody thought I was cheating. They were kind of kidding because they were my friends. But in general, you can expect to get 2 aces dealt 1 out of every 221 times. What if this had been 2 kings? Then nothing would have changed except the aces. The A's might be called K's. There would still be 4 out of 52 kings, and if you take one of them out, there's still 3 out of 51. So sampling without replacement is when you're drawing multiple times, but you're not putting things back. Without setting up the formula, what do you think you would have to do to calculate the probability that the first card is an ace and the second card is an ace? And let's say you get dealt a third card and it's also an ace, such as if you're playing stud, 7-card stud, where you're dealt 3 cards at the beginning. Well, these are still independent events, and this is still without replacement, which means every time something happens, I have to consider that it happened before setting up the next probability. Well, we already know that there are 4 out of 52 cards that are an ace, so let's pretend that I give you one of them. If I give you one of the aces, how many cards are left? 51. And of those, how many are aces? 3. And now I give you a third card. If I've already given you 2 cards, how many are left for the third card? 50. And if I've already given you the first 2 aces, how many aces are left? 2. That's even smaller. Oops. The probability of this happening is 0.000180995, or as a percent, 0.0180995%. So you can see it is highly unlikely that I'd give you 3 cards and they would be aces. It happens, it just doesn't happen very often. And we could do 4 aces. If we did 4 aces, do you know what the 4th fraction would be? Well, there would be 49 cards left and only 1 ace remaining. So getting 4 aces in a row, just divide that by 49 and it gets even smaller. So that's an example of sampling without replacement. In the next video, we'll take a look at a sampling with replacement.